So what I'd like to do is do a little bit of a deep dive. Maybe we'll do some review of some of what Rossen did, and then do a deep dive into how to take these streams, reactive streams, compose them, transform them, create them. So we're going to look into specific examples. But first we'll just go through some slides about the basics. So I think we're going to cover some of these basics in more depth than Rossen did. So this is the agenda basically. What is reactive? We're going to look into why we do it, how we do it. We're going to look at the basics of the flux. The flux is also an observable in the RxJava world. It's the same thing. It's basically a stream of data. We're going to look at marble diagrams, which is going to it's a way to interactively experiment with all of the reactive constructs. We're going to look at the difference between cold and hot fluxes. And then we're going to see some deep dive coding demos. And I hope people will participate with me on those. So what is reactive? It's an alternate programming paradigm. So, you know, I remember in college when we were learning about linear algebra, and it took algebraic objects like numbers, and it turned them into sets of numbers, right? Matrices of numbers. And it's kind of the same paradigm. Instead of dealing with single numbers or single data units, we're dealing with streams of data. And how do you combine those streams? How do you manipulate them? How do you extract the data that's coming out of them? They're high performance, so the whole reactive manifesto is about creating scalable systems and being able to have threads that are not blocking, being able to tell your server, tell your process, just exactly how much data you want to have and when you're ready to stop getting data. The tools are declarative, they're functional, and they're really easy to use, really cool. Even if you're not doing a reactive application per se, just the tools and the power of them is similar to Java streams, but really a lot more powerful. So by using these, you get a really concise programming paradigm. And it doesn't change from language to language too much. So we're going to see an example. You see, on the left we have a Java example. And I mean, the language in the world that's the least close, that's the furthest from Java, I would say, is Clojure. And if you look at it, it's really like line for line, very, very similar. So it's very much language independent. There's a spec, and all of the languages need to adhere to the spec. The original problem, I think, was stated by Netflix. And you know, when you go on Netflix, there's a lot of stuff going on behind the scenes. You got to get your queue. You have to get people that are similar to you, what they like. There are so many different. What are the recommendations that are specific to you as a user? So there are many different individual queries that are coming in that have to come back to you as a single query. So as a single result. So how do you compose all of that and keep track of all of those things? So that was, I think, the original problem that started this whole reactive movement. In order to use the Spring version, the pivotal version of reactive, that's called Reactor, you import the Reactor core into Maven. There's also a lot of testing tools, and you can get that from reactor.test, -test, and those give you the ability to compose these streams in a way that you can say what the timing is. You can specify timing, so you don't have to, let's say you have a stream that has an interval that's going to emit every second, and you want to wait 10 seconds. You don't want to wait actually 10 seconds on your server, so you could create a stream that pretends that it's waiting 10 seconds, but it's really just going instantly. Okay, so the basic model of reactive is that everything is a stream. Even a single object is a stream of one object. But they don't have to be just objects. When you think of Java programming, an exception is, you do this is the happy path, and then this is the exception. So exception kind of implies that it's an exceptional path. In reactive, you don't have that exceptional path. An exception is a first-class citizen. It's a stream. It's an event. It's part of an event in the stream. So you have a flux or a publisher. A publisher is the interface. Flux is the implementation that's wrapping a real stream or that is producing data that goes into a stream. and it is consumed by a subscriber. So the subscribers consume the messages. Fluxes are immutable, so every time it's kind of a monad. Every time you compose different fluxes or transform fluxes, you're producing new fluxes. Basically, the model works like this. A subscriber has these basic methods: on next, on complete, on error, and you can also use on subscribe. And the on next is represented in these marble diagrams using marbles. And then the on complete is represented by just a dash. And on error is represented with an X. Those are the events. We'll see more of those in the marble diagrams. You can create a subscriber. There are different constructors. The basic constructor, the full constructor, takes a, usually we use lambdas, so it'll take a lambda that tells you what to do with the happy path, a second lambda that tells you what to do on error, and the third lambda that tells you what to do when the stream is done, right, and on complete. The second two of these, the error handler and the end handler, are optional. So you could, in many cases, we'll just program the happy handler. Okay, and some of the transformations, they look like this, and you'll see they look very similar to Java streams. But we'll see also that they're not really very similar in the end. So you could have a filter. The filter says eliminate some, retain some, eliminate some, then you subscribe. Or you could have map, which transforms the stream. So you take input data, and then you transform it and produce an output. Or you could even have map and filter, right? You're filtering, you're saying, we only want these, I want non-null data, and then I want to map it to something else. You could also have, for diagnostic purposes usually, you could have a do on next, and you could print out a result, an intermediate result. Okay, we're going to take a look at the marble diagrams. Let me see if this switches. Okay. The marble diagrams are a website. Sorry. How do I transfer this? I'm trying to get out of the full screen mode. Oh, yeah. Okay, and why isn't that? It's not. I did, yeah.
It should be showing everything on your screen now. Maybe just unplug and replug the HDMI. For me, as long as I hit escape on the PowerPoint, it kept working.
Let's see. It's like we lost the signal.
Lose connection?
No, I don't think so.
Oh, there you go.
Yeah, but it's not. It's not giving me the website. Let's see if it's a. 1 second.
Do you still have PowerPoint open?
I do, yeah.
Where is it?
Maybe.
Like in presentation mode? Go to the actual presentation mode. Alt-tab a couple times.
Alt.
Get over to the one that's actually open and presenting, if you still have it, and hit.
Let me just see if we can do it with this.
If you still have like the F5 presentation mode open, it won't show.
I don't.
Oh, okay. Sorry.
Oh, okay.
I'm not sure. Okay.
Sorry, folks, 1 second.
Probably skip this one if we don't.
Oh, there we go.
Oh, good, okay. The only problem is, let me just.
That should just mirror.
Okay, that's better.
Cool, okay.
Thanks.
Yeah, sorry.
Okay, so there's a really cool website called rxmarbles.com, and it displays these interactive JavaScript versions of all of the manipulation and the transformation and composition functions of the observables. The observables are the word observable is used in the RX Java world, but it means the same thing as a flux in the Reactor world. So, for example, this is a merge. We have two streams, and what merge does is it combines them into a single stream. But they're interactive, so you can move these things around, right? And let's see some of the basic ones. Like you have a debounce. In the Reactor world, it's not called debounce, it is called sample timeout. So what it does is it looks at a group that are very close together, and it just retains the last one of them. Let's watch if I move this away. You see, it gives it its own life. So anything that's close together, it combines them, and it just retains the last one. There's also a zip operator, and we're going to look more into this, so we should just become a little familiar with it. The zip operator takes two or more streams, and it combines the results of them according to a combination, a mapping that we provide. So in this case, it's just creating a new marble that has, like over here, we're emitting 1, 2, 3, 4, 5. On the second stream, we're doing A, B, C, D. So the combination will be 1A, 2B. Now if we move this over, see what it does? Now 1B, 2A, it keeps things in sequence. So it's actually sequencing the two streams and combining them. As soon as any one stream terminates, which you see this one has, the top one has 5, and the second one has 4, so the result has 4. As soon as one stream terminates, the whole zip operation terminates. So you could have an infinite number of items coming out of the first stream. As soon as the second one terminates, you're only going to have the many of the second stream. So there are many different operations like that, and you could try them all, and it's pretty cool. Like over here I see I'm skipping 2. So I have an input stream that has 4 events. I'm telling it skip 2, so I'm only retaining the last 2. It's very good to play with this if you're trying to experiment or just see what there is, really. There are so many different combinations of things. This doesn't have everything, but it has a lot. And so you could kind of think out loud using RX marbles. Okay. So we already looked at merge, we looked at zip. There's also a transformation called first emitting. Let's say I'm in the financial industry, so we might have feeds coming in from Reuters and from Bloomberg, let's say, and we just need a quick feed, so we'll pick whichever one responds first. I don't care which one, I want one. So look at, kind of test Reuters, test Bloomberg, whichever one comes first, that's the one I'm going to stay with for a while. So that's what first emitting does. It just picks the first stream. There's many of these decision operations that help you decide which elements to pick from which stream or which streams to pick. So in order to create a stream, there are many different operators. The just operator produces a stream that emits just the supplied value. It's overloaded, so you could take a varargs and provide more values, but it emits one event for each one of those values. If you have, let's say you have an array or a list and you want to emit all of the values, you want to transform that collection into a flux, they have the from iterable and from array methods that you could use that to transform your collection into a flux. There's range, which produces, let's say I say range of 3, 7. So that'll produce a range from 3 to 9, 3, 4, 5, 6, 7, 8, 9. 7 items starting from 3. Also, the unique thing about observables is that there's a temporal component to it. So it's not just like data that's all there at one time, the way in Java streams are. In observables, in these streams, there's a temporal component. So I could say emit this, an event comes out now. Now 5 seconds later, another event comes out. 2 seconds later, another event comes out. And we're going to see in the examples, when we get into the examples, how you can actually compose these streams with different temporal components. Okay, these are some of the transformations. So we looked at skip, and there's take. So you could say only take the first n components. You could say transform a stream, only return a new stream that has distinct. So I could say, let's say I have 1, 2, 1, 2. It'll only return 1, 2. It distincts out the rest. I could have distinct until change, so it'll eliminate adjacent repetitions. There's filter that will filter out based on a certain condition, and it'll only return the things matching that condition. There's map. Map says take an existing stream, take the events in that stream, transform them in some way, and produce a new stream with the result. And then there's flat map, which is really kind of interesting. Flat map takes a collection of stuff, transforms everything in that collection to an individual flux, and then produces a large flux with all of those smaller fluxes in it. We'll see an example of that. It's a little hard to get your arms around. Okay. A lot of people, the first time you see and you start working with reactive and with fluxes, it looks really similar to the Java Streams API, but it's really very different. Java Streams are pull-based, so basically you're iterating a collection, and you're saying, okay, give me the next element, do this. Give me the next element, do that. Reactive Streams are push-based, so you're just sitting there. You have your listener, your subscriber, and as things come, the subscriber is responding. Java Streams may be very powerful, but essentially they're just a way to iterate collections or arrays, right? Whereas with reactive streams, it's really a way to attach to real-time feeds. Java Streams are generally synchronous. There are exceptions, but when you think of Java Streams, they're synchronous, whereas with reactive, as we saw in Rawson's presentation, they're very much concurrent, and there's flow control, there's back pressure. Java Streams, once you use them, they're done, right? You can't have different things listening to the same Java stream, whereas with reactive streams, you very much can have concurrent subscribers doing their thing. With Java Streams, there's really no composition of streams, no concept of zip and merge and all these things. Whereas with reactive, you have a very advanced composition and transformation functions. And Java Streams are basically finite, right? You're iterating a collection, a finite collection that has a size, whereas reactive streams never have to end. Also note on concurrency, just in general, when we as Java programmers deal with concurrency, we have to make things volatile and deal with the specific concurrency concerns. When a subscriber is receiving notifications from a stream, those are guaranteed to come in synchronously. So you don't really have to be defensive in your coding. As you process something, that is thread safe. There's a distinction that we're going to look at between cold fluxes and hot fluxes. So a cold flux is basically producing a fixed amount of data. Every time a subscriber comes, if the stream, let's say the stream has 10 elements or 100 elements, a new subscriber comes on, it gets all of the events starting from time 0, so it gets the first event. A hot flux, a new subscriber comes in and it just gets the latest data that's coming in. We're going to see examples of that. And we'll see an example also of this. In order to transform a cold flux to a hot flux, you have to call the publish and connect. We'll see that. So now we're going to look at an actual demo. IntelliJ. Okay. It's way too small. Sorry. Okay. Okay, so the way this is going to work is we're going to look at individual, this is a JUnit tester, so we're going to look at some individual tests and we'll gradually compose different fluxes to get some experience with that. One thing about fluxes is in certain cases they'll as soon as they terminate, the application will terminate. So we don't want that to happen because we want some of these to keep running. So let's just, since it's a JUnit, we could have an at after. And we'll sleep for 15 seconds. Okay. Okay, so let's set up a basic flux and just see how that works. So the method we saw for creating a flux is the just method. Let's produce a nice little single emission. Okay, this is how you produce a stream with one emission. And we're going to just produce the word howdy. Okay, seems like nothing's happening. Does anybody know why? We didn't subscribe, right? So let's subscribe to that. And now we should print out our single emission. And we see that works. Now, this, as I said, it takes a vararg. So let's say we want to have another emission, and that's going to call howdy world. Let's run that. And we see that we got howdy world. Now, let's say we want to have a collection. Let's start a new tester. Okay, so I have this collection of words. And this, when I was a child, I learned if you learn how to type this sentence, then you've covered every key in the keyboard, right? The quick brown fox jumped over the lazy dog. So let's see if that's really true. We want to see if we have 26 of those. And we'll see a couple of the constructs, the important constructs on the way. Before we actually get to this, let's just look at the range construct. So let's say we want to create a flux, and we want to have integers. I'm going to call this, let's call it lines, equals, and we'll give it a range. So we'll say flux range. Yeah, can't type. 0 to 5, and of course we have to put a subscribe. We have to subscribe to that, so we'll say lines dot subscribe. Let's have a, okay, and let's see how this works. So we see we got 0 to 4, right? Because we started it from 0. I really wanted to start it from 1, so let's try it again. Okay, 1 to 5. Now, you could go to make a pretty big stream out of this by putting max value, right? That's never going to end until it gets to that billions and billions, and we see that it does. Okay, now let's look at the words and create a flux of those words. So we saw the just method, and let's put the words in there and see what happens. Okay, so I'm taking that list. Now, it seems to work. Did anybody see anything wrong with that? It's just one, right? It's playing the whole list as a single item. That's not what we wanted at all. So what we really wanted was not the just, but the from. From, they used to call it just from, and it was overloaded, but now it's called from iterable. And that correctly produced the quick brown fox jumped over the lazy dog. Okay, now let's say we want to number these. We want to put line numbers on each one of those. So we want to combine the lines with the words fluxes. So let's take, we want to zip those, right? And we use a zip with operator. And we'll take a word. We have to create a lambda. So we'll take a word. We're zipping it with line. And from that, we want to produce a, we want it to output, let's say, the line plus space plus the word. So that should effectively combine those two things. Oh, I forgot to put words. Okay. Sorry. Zip with words. And I'm combining the word and the line. What did I do wrong here? Word, line, line plus word. Zip with, I'm sorry, you're right. That's right. Sorry. Okay, so we should be able to combine those. And we see that it added the line number. So it effectively took two streams and it combined them into one. That's great, but let's say our goal was to count letters, not words, right? So how do we transform these into letters? So what we want to do is we want to split all of these letters, all of these words into letters, and then we want to take all those splits and combine them into a single observable. And in order to do that kind of thing, where you're converting a lot of little things into a lot of observable things and then recombining them, you use a flat map. So we want to take the flat map, and what we want to do is we want to take each one of those words, and we want to transform it by splitting it. So we'll say word split, and we do that, and that splits it into letters. Now this is giving an exception because that returns an array, and we really don't want an array, we want a flux. So let's do a flux from array. Okay, and that should, so this is going to split each word coming in, it's going to split it into its component letters, and then it's going to create a new flux from those, and then it's going to map all those together into one single flux, and then it'll zip those with the line. So let's run that and see how it works. So it looks pretty good so far, right? The quick brown fox. So we actually did split things into letters, and we see we have 36 letters. Now, those are not distinct. So let's distinct those and just make sure we have got 26 of those, right? Because we want one for each letter of the alphabet. Huh?
I think you're missing an S.
Let's try. Okay, so over here we have 25. So something is going very wrong. It's hard to tell because things aren't in order. So let's order them. Okay, and we'll check. And now we could see that actually John is correct, and it's RT, it's missing the S. So let's correct that, and I think I was wrong when I was a child. It should be the quick brown fox jumps over the lazy dog's back. And now we have 26, and we have all the letters accounted for. So you see that it's a powerful paradigm for transforming and combining streams. Okay, now, as I mentioned before, there's a temporal component also. So let's try to see if we could take advantage of that. Okay, so again, I'm in the financial industry, and we pay for the data that's coming in. So we want to make sure that we're not paying too much by asking for too much data when it's not needed. For example, let's say on the weekend, you want to get your pricing feeds much less than during the week, so to give a contrived example. So you have to have the ability to control that clock. So let's just see how we would do that over here. So let's create some clocks here. Let's create a fast clock, and it'll be a clock that just emits a long every once in a while, and we'll call it fast. And we'll let this produce, we'll use the interval operator, and the interval operator says emit a long every n units of time. The way you do that is you have to pass in a duration, and we'll say duration of seconds, we'll say every 1 second. Okay, it's going to be a fast clock. And we will subscribe to that clock, and we should see an emission every second. Let's see how that works. So it looks like it's working, right? Now let's make a slow clock, and we'll see if we can combine those. And we'll make that, instead of every second, we'll make it every 3 seconds. Let's just see if that works. Okay, so it does indeed seem to be waiting every 3 seconds. Now just for the fun of it, let's, instead of my stock example, let's just make an emitter that emits the time, the current time, every second. So we'll call it a flux. Going to do a local date time, and we'll call it date emitter. Okay, and we'll get it, let it transform. We'll let it emit every 1 second. So we'll say duration of seconds. And every second we'll emit a date. And let's just do our, okay. This is not working yet. I didn't finish it yet, because what I really need to do is I need to transform those. So now I have the interval, but I need to transform those, because this is emitting longs and I want to emit dates. So so I have to map that. Let's put it on, I think traditionally we do these things on separate lines. And I want to say, okay, now for each tick, I really don't need the tick, but what I do want is a new date. So I'm going to say local date time now. Okay, let's just make sure that thing is working. So now I have 3 streams here, but I'm only subscribing to the last one. Okay, so indeed, it looks like it's emitting a new date time every second, right? 1, 2, 3, 4. Okay. Now let's say I want to make this emitter do exactly what it's doing, except I want it to, every few seconds, I'll change the pace of it, kind of a syncopated clock. So for a few seconds I want to go fast, and then for a few seconds I want to go slow. So let's see how we're going to do that. So let's take our fast clock, and let's filter that. We're only going to take the ticks that are ticked when the time is a fast time. And I created a little convenience method called isFastTime. And that's basically every 3 seconds. It just mods the time. So I'm going to say if it's fast time, that's when I want the fast clock to filter. And let's just subscribe to that and make sure that that is doing what we expect it to do. Get rid of that. So it is indeed emitting every 1 second. Now let's take our slow clock. Well, let's just do this all at once. So we're going to do a flux, and we're going to merge these 2 clocks. So I'm going to merge the fast clock together with the slow clock. And the slow clock I'm going to filter so that it only comes out at the slow times. I'm going to take the tick, I'm going to see what time it is, and if it's a slow time, I'm going to emit that. Okay, and then let's subscribe to that and see how that looks. So this should go for a few seconds fast and then a few seconds slow, and let's just get a feel for that. Okay, it started again at 0 because it's a different clock. Okay, so we see it seems to be working. It should speed up now. Okay, so you see how you get that syncopation where it starts emitting the slow and then the fast. Now let's combine that with our date emitter. Okay, and let's just call this one clock. Okay, so we want to combine this clock with our date emitter. So what we want to do is we'll take the clock and let's try zipping it with our date emitter. And basically what we want to do is we want to take a clock tick and a date, and we just want to display the date. And we'll subscribe to that. Let's see how that looks. So this should emit a date every second for a few seconds, and then a date every 3 seconds. So let's see how that looks. So it seems to be working. It's slowed down. Does anybody see anything wrong with this, though? It's a sequence. It's not, it should be doing the current time, not the... it's going 31, 32, 33, 34. It should show the actual current time. So we really don't want the zip function. What you want, because remember, the zip function always takes things in the original sequence. What we really want is with the latest. So with the latest from says, okay, with every clock I have, see what the date emitter is up to and pick the latest value from the date emitter and then zip those together. So let's see if that works. 16, 17, 18, 21, there we go. Okay, so what this is showing us is it's showing us that we can kind of combine, different streams into a single stream, and that there's a temporal component. For my last number, let's see how we attach to an existing feed. So just for the fun of it, I created some feed, and I called it some feed. This is not a reactive version. So let's say some feed. This is how you would do it traditionally. Equals new some feed. Okay, this is a feed that's emitting stock prices. Now normally I'll create a listener, and I'll say it's called some listener. L equals new listener, new sum listener, and whenever there's a price tick, I want it to do emit the price tick. And if there's an error, for the fun of it, I'll emit the error. Okay, and then of course I have to add the listener to the feed. So I'll say feed register L. Now this is the old way of doing things, right? And let's just see if that works. So we see that it works. But how do I attach that so that that feed becomes part of the reactive, becomes reactive? So let's get rid of all of this. And the way you do that is you use the create. So we'll take our, we'll take a flux, and we'll call it flux feed. Flux feed. And we'll say flux create. And now create takes a lambda, and the first variable of the lambda, the parameter of the lambda is an emitter. And now you have to say what you want that emitter to do. So what we want to do is, first of all, we want to create a new listener. So we'll say, basically write all this code into here. So we'll say we created a new listener. We're going to, instead of printing this out, we're going to say take the emitter, and we're going to call the next function on the emitter, and we'll give it the event. Okay, now the emitter understands that it's an event emitter because of when we created it against this new feed. against our feed. When there's an error, we want to do emitter error, and we'll pass in the throwable. And then we want to register that listener and add it to the feed. Okay, that's done. So now we have a flux feed. Now what should we see here? Nothing, because we didn't subscribe to it. Now one other thing is, normally with a feed like this, you want to make sure that you're getting the latest data. You don't want to go back in time and get the old data. So in order to do that, we have to publish it and create a hot observable out of it. So we're going to create a publisher, and then you have to connect to that publisher. The publisher is called the connectable flux. Then we're going to say publish, since it's connectable, we'll connect. And then we can subscribe. Okay, and now new subscribers could come along and they'll be able to get the latest feed, not starting from the beginning because it's a hot observable. So we've seen an example. So this is giving us an example of how to take an existing feed and transform it into the Flux observable framework. So basically that's the presentation. What we've seen is, we've seen that a flux is a stream of data. It has a temporal component. Different fluxes can be transformed, composed, and used to create new results for your application to make them reactive. Any questions?
If you have the historic stream, and how do you recover this? Is there any way to recover the historic data properly? Like in Spark streaming, for example, you'd have checkpointing and stuff like that. Do they have some form of thing like that?
If you have to be careful when you do that, though. If you have a historic stream, you have a lot of data. You want to be able to get rid of that data, right? You don't want to buffer all that. Yeah. So you can transform that. When I created the hot observable, you still have the cold observable there, and you can still manipulate that by throttling it and getting rid of earlier.
If it crashes though, and you have to bring it back up,
yeah,
resume from a certain point.
You have to code for that.